Alright, let's go ahead and do number 5. This is on page 194. Alright, the number of customers waiting for gift wrap service at a department store is an RVX with possible value 0, 1, 2, 3, 4 and corresponding probabilities 0.1, 0.2, 0.3, 0.25, 0.15. A randomly selected customer will have 1, 2, or 3 packages for wrapping with probabilities 0.6, 0.3, and 0.1 respectively. Let y equal the total number of packages to be wrapped for the customer waiting in line. Assume that the number of packages submitted by one customer is independent of the number submitted by any other customer. Okay. Determine P of x equals 3, comma y equals 3, i.e. P3, 3. Okay. First we need to figure out, what we're given and model the situation. Alright, so we are given an RV x, and then that RVX is going to take things from whatever the outcomes are in our sample space to the set 0, 1, 2, 3, 4. Been a week, but I think this is the proper definition, right? It takes in from the sample space and it assigns them a real number value. Yeah, I think that's it. So that would be x, and this is supposed to represent this had corresponding probabilities 0.1, 0.2, 0.3, 0.25, 0.15. Yeah. And then we say x represents the number of customers waiting. And then we also have an RVY, which takes from whatever sample space we got and it maps it to, 1, 2, or 3? This is the number of packages, I guess, and this is 0.6, 0.3, and 0.1. Okay, and then so y represents the number of packages to be wrapped for a customer. Alright, so it's asking us to determine, we want to know the probability that x equals 3 and y equals 3. And we know these are jointly distributed. So let's make a table like this. Probability of x, y, and then let's have this, let's see here, let's have x be over here, and we'll map this out to be 0, 1, 2, 3, 4, and we'll have y up here, and we'll map this out to be 1, 2, 3. So, yeah, that's kind of because the number of packages submitted by one customer is independent of the number submitted by another customer. So, X represent the number of customers waiting. And Y represents the number of packages to be wrapped for each customer. Then we know that as we know in general, we know that, is it saying that X and Y are independent? Or is it saying the number of packages is independent? The number of packages is independent of the number submitted by any other customer. So does that mean X and Y are independent, even when I'm trying to think of? X represents the number of customers waiting. Y represents the number of packages to be wrapped for customers in line. We want to know if there are 3 customers waiting, the probability of for cut and so why is the total number of packages to be wrapped for the customers, it should be an S, waiting in line, and the number of packages is independent of any other submitted. Okay. So we want to know the probability that we have 3 customers, and Y represents the number of packages. Well, if there's 3 customers, and each one, I don't know, there are 3 customers, and each one is independent. So you have, this is independent of the fact of each customer itself. It's independently going to determine, what do you call it, the number of packages. Probability that X equals 3. probability that 3 customers are waiting and 3 packages are to be wrapped. This is so confusing. So basically, we just assume we have 3 customers waiting, and if we have 3 packages. That means if the options are, if every customer can choose 1, 2, or 3, right? Every customer can choose a number. They can't choose 0. They can choose 1, 2, or 3. And there are 3 packages to be wrapped. Then every customer must have 1 package, right? And since this is independent of each other, and we know that there's a 0.6 probability every time that they're actually going to have 1, then this probability had to equal 0.6 cubed, right? So the probability of 3 had to equal 0.6 cubed. And that is going to be 0.216. Okay. So the probability that we have a 3 and a 3 has to be 0.216. Right? Just set this up. So, hold on a second. So is Y the total number of packages to be wrapped? Okay, so just another probability happening. A randomly selected customer will have 1 or 2, 3. I thought this one. Oh no. Okay. So what's happening is we did the X correctly. This is from whatever sample space to 0, 1, 2, 3, 4, and then 1, 2, 3, 0.25, and 0.15. Okay. So overall, the overall chance here, or the overall number, the chance of these numbers of customers waiting, we know that X represents the number of customers waiting. Alright, so we know that this is correct, I think. And then the Y is not correct. because what it's saying is that each so any customer in particular, any customer will have I have 1, 2, 3 packages with probability 0.6, 0.3, and 0.1, but this is not y. So so how do we represent this symbolically? I don't know. We're just gonna go ahead and keep moving to y. So y is the total number of packages for customers in the line. That's going to be the key right there. So any individual customer will have 1, 2, 3 packages, and then y is the total number of packages per customers in line, which could be as many as 12. For this one, y is going to be a random variable that defined from whatever a sample space is, and it's going to assign it from 0, 1 to ... to 12. And then it wants to know the probability that x equals 3, y equals 3, and they're saying that this is the probability of 3, 3. Okay. So this is the correct setup. And these probabilities, they're not given, we have to find those out. So you can think of it in this case, the probability that we have 3, 3. Again, it's the same what we were just talking about with the 3 people in line. The 3 people, so these are people, and we have 3 presents. Then we know that each one of them must have been 1. So this is going to be 0.62, which was what was it? 216. 216. Okay. Which is 0.216. So I believe we have the probability of 3 and 3 correct. So we were to make a huge big table out of it. 3, 3 would be 0.216. So now it's asking for the probability that x equals 4 and y equals 11. Yes. Okay. On this scenario, there's 4 people in line. And draw a picture. 1, 2, 3, 4 people waiting in line. Oh no, this is going to be a combination problem, isn't it? And I want to know basically the number of ways I can get 11 presents. So this can be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Well, the one thing we know it's not going to be is 3, 3, 3, 3. We can take that off the table. So here's the great. Do a combination. Let's see if they have any good formulas for us here. A be any set consisting of pairs x, y, such x, y equals 5, and the probability of x, y in general by summing the joint PMF probability match function over pairs in A. Man, this is let's see here, drink some coffee. Okay. Oh man, okay, I'm thinking on the top one, did we have to okay. So we got 3 people, 3 presents. 1, 2, 3. The prob So do we have to consider this right here, that point, there's a 25% of this unique scenario happening? And if this unique scenario happens, the probability of getting this, oh no, it has to be multiplied by 0.25, doesn't it? Okay. Okay, that's better. Okay. All right. So this, yeah, that's it, right? Okay, so let's just do the same process here. So let's assume that this dude had 3 packages, 3, 3, 3, 6 to 9. And this dude could have the possibilities of having 1 or 2. I mean, they're talking about the independent. Just a shot in the dark. Would making a table here be something sustainable? Yeah, 0, 1, 2, 3, or 4. And these are x's. Now, y is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. X equals 4 and y equals 11. No. Would it be something like where you have 0.15 times the probability that y equals 11? And would that make every table we can? Because I'm confused about is that we know that because if x and y are independent, we know that the probability of x, y going to be the probability of X times the probability of Y, right? So we know the probability of X. So the probability, so I don't know if they're independent. But saying that the number of packages by any one customer is independent of the number permitted by any other customer, but is the X. The X independent. The number of customers waiting in line independent of the number of packages that the customer is going to choose. Let's assume they are. Then the probability that Y is 11 in general. Probability which is the probability added up over everything, right? So the probability that I have 11 customers, sorry, hold on, why the total number of packages? But the probability that I have 0 customers and 11 packages, it's not possible, it's 0. The probability that I have 1 customer and 11 packages, it's not possible, it's 0 too, right? And then the probability that I have 2 customers and 11 packages is not possible. And the probability that I have 3 customers and 11, it's not possible either. Right? Because 3 times 3 is 9. You can only have 9 packages at the maximum, right? So you must have 4. And therefore, the probability that Y equals 11 is simply the marginal probability that of Y equals 11. Because if we focus on this margin, right? What is it? Two random variables are said to be independent if for every pair of X and Y values, the probability of X and Y is equal to the marginal, that's marginal, right? Marginal probability, something like that. It's equal to the marginal of the X times the marginal of the Y when X y are discrete and monadic continuous. So the marginal for the x it has to be 0.15, doesn't it? Times the marginal for the y. So with this, the marginal and yes. I mean, so maybe if I know the whole, because this would be 0, 0, 0, 0, and then this would be okay. So if we know that the probability of any of these 1, 2, 3, we know there must be 4 customers waiting, right? We know that these must have 3, 3, 3. And then we know that this can be 1, 2, or 3, right? So this must be 2. And then this must be 0.1, 0.1, 0.1, 0.3. And you multiply all these together to get that probability. Okay. Get 3 times negative 4. Okay. So the probability that y is 11 can only be this option. So it must be 0.0003, right? So this must equal. Okay. 1, 2, 3. That it? Okay, I really hope so because I can't. I'm not sure. I'm a little scared to check out answer, but let's go check them. Let's see if we got. This is chapter 5. No. This is 0.054. Okay, at least we got that right. And then we got 0.00018. How do we get 0.001? Okay, I don't know how I'm going to do this, but I think this book has not been trustworthy in terms of its answers. It's gotten many of them wrong. So what we'll do here is I'm going to actually see if we can do an upload here. Okay, so I'm going to send this to my Google Drive and put this into my specialized chat GPT that I use to develop on these concepts. Let me get my computer here up and going. Okay, download that file. Let's see here. We'll see what the GPT says to do, and then you can kind of compare that what we did and see if we're in agreement. Kind of GPT is looking at as well, so it's something we need to watch out for. But there it is. Being very slow today. Come on. got the file. I'm going to open up my GPT now. It's specifically designed for tutoring for machine learning, mathematics, and probability, that good stuff. So we're going to try to okay. So okay, I see. So it looks like we needed to include a combination. Because it's saying that it wants it to be multiplied by 4, 1. But so saying that basically we were looking at it as unordered, 3332, but it's saying the order does matter, which I guess it does. Yeah, I guess it does. So 410.00045 would give us the answer of 0.00018. So basically, the position matters, because you can have 3323, 3233, all that. That's why I'm studying this. This is my weakness area. So that's why I'm trying to get the probability stuff down. Anyway, I think that's good for today, I think. Thank you very much for watching. See you next time.